kind of a Fourier decomposition.
It kind of is, but we found a way to do in seconds what other people were doing in hours.
So, so a fast Fourier.
Yes, it was a very fast
decomposition. Interesting. Maybe we'd have to have that talk sometime.
yeah.
He's also, of course, an amateur astronomer. He's had a very long association with the Los Angeles Astronomical Society, and I believe you're president now.
I am for the 11th non-consecutive year.
Oh, I don't want to hear that.
And is also seems to be the one who gets people on hook to give talks to them. And many of you will recognize him also from his affiliation with the Mel Wilson Institute. He gave us an outstanding tour of the observatory. That would have been about 2 years ago now. So let me turn the lectern over to Mr. Tim Thompson.
Oh boy, thank you. Well, I just put this up here to point out that there are quite a few books. I put 3 of them up here. The Hidden Figures was a movie about the NASA women who did computations that kept rockets from crashing. And JPL had its own crew of computers that have their book now. I'm not going to be talking about the new women, see, because they're, but I am going to talk quite a bit about the Harvard computers in Donna Sobel's, the materials in Donna Sobel's book, and a lot about women from old history and centuries past who have blazed the trail so that the Hidden Figures and Rocket Girls women could actually do something. Somebody had to start the ball rolling somewhere. And so I'm going to start kind of at the beginning. I just want to point out that if you look at the literature and the art, the allegories for science, there's always women involved. This was the 1300s where a woman is represents the knowledge of geometry and mathematics and is teaching everybody else wisdom. And here we have science is depicted as a woman exploring the world as time sweeps the rugs away. And this is from a mission ticket from the Laverian Museum in the 1700s. And this, of course, is much older. But despite this fact that women always, that science and wisdom and knowledge always seem to show up feminine, when the real women try to live up to these expectations, now, history has not always been terribly kind to them in that regard. But once in a while, so Juliana Morel is the first woman to receive any kind of doctoral degree in the relatively modern sense, a doctorate of law, in 1608. And if you do the arithmetic, you'll notice she got her doctorate when she was 14. And Elena Lucrezia Piscopia, she's the first woman to be given a PhD, that's a doctor of philosophy. She wanted to get a doctorate in theology, and the cardinal, who was the bishop of Padua at the time, stepped in and said, "Oh no, we don't let women have degrees in theology. That won't. But you can have a degree in philosophy. That's okay." And so they gave her a degree in philosophy. So the first PhD. Both of these women were incredible geniuses by any standard. As you can see, Morel got her doctorate at the age of 14, defending a thesis in a room full of educated and literate men on law and ethics and Aristotle, and then ignored several attempts by filthy rich men to marry her, because that was what people did at that time. And when she was 16, she signed on as a Dominican nun, and that's that. And she just went to the convent and stayed there and studied. And Elena, by the time she was 7, she could speak 6 or 7 languages and had already mastered much of philosophy. And by the time she was a teenager, she had mastered several musical instruments and just about everything that was known about music at that time. She got tired of that and then took up Aristotle and philosophy and all that, so eventually they gave her her doctorate. But she died, unfortunately, young from tuberculosis. But both of them were child prodigies, really brilliant, and probably the reason they were able to get the degrees they did is that both of them were from upper class families. They stood out. The people in charge of things knew who they were, especially Elena. And so it was a little easier for them to rise to the top than it would have been for a peasant or a woman without necessary social connections. I'm going to fast forward to somebody you've never heard of before, probably, Maria Kunitz. Kepler, of course, you've heard of, Johannes Kepler, and since my cheap little laser pointer failed, I'll use my 20th century Johannes Kepler up here. I've got it sitting right here, but this actually shows up better. Yeah. Everybody knows who Johannes Kepler is, of course. He's the one who figured out planets move in elliptical orbits, and he wrote the Rudolphine tables named after some king or prince named Rudolph, so that you feel important, that allows you to predict the motions of the planets. But he made a few mistakes. Maria corrected his mistakes. He's famous, she isn't, but she corrected his mistakes. But probably most important, not only did she correct his mistakes, she made it possible for other people to read what he wrote, because for one thing, he wrote it in Latin, and most people didn't read Latin, and his mathematics was pretty cumbersome using logarithms. So really to follow Kepler, you needed to know some advanced math, you needed to be able to read Latin. So she wrote it in German so that ordinary people could read it, and she got rid of the logarithms and changed the mathematics to something easier. So you still had to know some math, but you could step down a notch, and people who didn't have that high an education in math could follow it. So she made it accessible. But writing it in German is the important part because there was no German lexicon for science at the time. Nobody wrote science in German. They wrote it in Latin, so she had to make up a lot of it. And so she's actually responsible for the roots of scientific jargon in the German language. A lot of it comes from Maria Kunitz originally writing Kepler in German.
Do you want a laser?
I've got one, thank you, but
Oh, you like that one?
yeah, this is old school,
Okay.
and if you can tell that I'm not a young school kind of guy, right? So, and so I got this at a teacher's math conference. It's one of the freebie giveaways at one of these things. And it's got a little finger on the end of it, right? Finger up the nose, all that good stuff. So it's a really handy thing to have.
Because the batteries don't run down.
That's right. The batteries in this thing are really good. So, the Marquise du Châtelet, she was an interesting woman who basically, like typical women of the time, she was self-educated. Did a lot of reading and poetry and science, but she's particularly interested in math and science. She translated Newton's Principia into French from Latin, the third edition, and it's still considered the standard translation today. I don't know if anybody's bothered to do another one because she kind of did the best job there was. And of course, like most translators, she added her own notes to the translation, and amongst her notes is the first real discussion I'm aware of conservation of energy in a modern sense. Energy does not show up well in Newton's original writings, which have more to do with force, and energy is kind of a nebulous concept. He's talking about forces and accelerations. So other people kind of suss energy out of his writings, and usually it's kinetic energy of motion. This idea that there's a total energy and that you can conserve it. It's kind of radical and new idea that she came up with. Now, she too was from an upper class aristocratic family, and everybody knew her, but she was a woman. And so not only was she not allowed to be a member of the French Academy of Sciences, they wouldn't let her in the room at all, because no women were permitted in the room during the meetings, nor were any women ever permitted in the coffee houses where the men discussed philosophy and math. And so she tried to follow one of her teachers into the coffee house once, and the men were like, oh no, we don't let your kind in here, and the teacher, but not you. So she got frustrated and simply showed up at one of the coffee houses and at the Academy of Sciences dressed as a man. And so they all know who she was, and they were like, okay, well, she walks through the door, we'll look the other way. And that's how she got herself into the meetings, by dressing as a man, thoroughly frustrated. And she was a friend and romantic liaison and collaborator with Voltaire, who said she was a great man whose only fault was being a woman. And very often in the literature, she's referred to as Voltaire's, like secretary, assistant, helper, whatever. She was actually a collaborator on an equal footing with Voltaire. They worked together and wrote together and had a good time together. And she corresponded regularly with all the great mathematicians at the time, Gauss and Euler and all those guys. She just had to dress like a man in order to get in the door, that's all. Now, while the French seem to have a problem, and you'll see they have a bigger problem later on with smart women, the Italians kind of don't. Laura Bassi received her doctoral degree from the University of Bologna, the second woman after Elena Piscopia to receive a PhD 54 years later. But she taught mathematics and what they called experimental physics and philosophy, which really is Newtonian mechanics, is what it is, almost like mechanical engineering. But she also taught Franklinian electricity, which shows up almost nowhere. People forget that our founding father, Benjamin Franklin, was one of the most respected scientists in the world at his time. A member of several of the international societies, had a big reputation around the world as an experimental scientist. And electricity, as Franklin had exposed it, was really kind of a new science and a new idea, and people were teaching that where they felt like they wanted to teach the upper class stuff. And so she was one of the first to get a hold of Franklin's writings and teach about his discoveries of electricity in Europe, in an Italian university. And Maria Agnesi was the first woman to be appointed a professor of mathematics, and the second woman to hold, behind Laura, to hold a university faculty position. Laura taught classes and appears to actually have taught men in her class, which must have been really scandalous at the time, having a woman teach men in the university class. Maria did not evidently teach any classes, but she did a lot of writing, a lot of research in mathematics. She wrote the first handbook on mathematics to be written by a woman, and there were mathematics books obviously written long before that, but she wrote the first one to be written by a woman, and hers was the first mathematics textbook or handbook to discuss both differential and integral calculus together in the same book. Derivatives, integrals, they're kind of, the opposites of each other. They go together. It's kind of hard to study calculus and do one without the other. So she put them both into a book. And her name, you'll find it in modern mathematics because of a curve, a kind of a peculiar cycloid curve that looks like this, called the Witch of Agnesi. And the reason it's called that has nothing to do with her personality. It's because some British guy couldn't read Italian right, and he mistranslated a word that meant something else as a similar word that said witch, so I called it the Witch of Agnesi, and that stuck. And so, as mistranslations, you see that all the time in academic literature. It's amazing. So, Caroline Herschel, okay, the top of my slide is cut off here, but that's okay. Caroline Herschel was Frederick William Herschel's sister. It was his assistant. And did lots of observation and discovered one comet on her own. Her great claim to fame comes in two stories. First, she was granted an annual salary of 50 pounds by King George III. That's the same King George we kicked out of America in 1776. But he gave her an annual salary, 50 pounds, which doesn't sound like much. It translates into about $5,600. 2016 dollars, which is still not a whole lot of money by our standards, but by the standards of the day was quite a bit, which makes her the first woman to be paid in world history for doing scientific work. So those women amongst you who are getting paid, That's why.
Mm-hmm.
Yeah.
On your previous slide, you had women who were professors. Those were non-paid positions?
They were teaching. They were paid to teach. So they weren't paid to do scientific work. They did it, but that's what they got paid for.
Okay.
She got paid for helping her brother. So it is kind of one of those splitting hairs, but we do that a lot in history. And along with Mary Somerville, she was elected either a member or an honorary member of the Royal Astronomical Society in 1835. Different sources give different levels of membership. Considering the year, I'm tempted to believe this was an honorary membership because they probably would not have granted full membership to a woman in the Royal Astronomical Society at that time. It's possible they might have, but I tend to suspect that they were both promoted to honorary membership status. And Mary Somerville, she became famous, again, for translating, just like the Countess du Châtelet, who translated Newton. She translated the Mécanique Céleste. It's an enormous 5-volume, I think we have 5-volume work by Laplace, which is really the first full exposition of celestial mechanics, orbit calculations, that kind of thing. Translated it into English, and as she said, she translated his work from algebra to modern language so people could understand it. She's the one who first speculated on the hypothetical planet perturbing Uranus, which caused John Couch Adams, that's the way he pronounced it, to go looking for it theoretically. And so Adams and Leverrier both predicted where Neptune should be at the same time. Adams told his boss, who told nobody else, and Leverrier told the French Academy of Sciences, and they told him to get lost. So he did something that seems kind of peculiar for a Frenchman at the time. He actually got in touch with a German astronomer named Gale. You look for it. The French aren't interested in looking for my planet. You look for it. And he and his assistant found it within an hour of starting to look for it, right where Leverrier said it would be. So the English, the French, the Germans, and of course the French and the English almost went to war after that on who ought to get credit for discovering Neptune. Claiming the French said Leverrier and the British said Adams, and nobody bothered to notice that it was a German guy who actually discovered the planet with his telescope. They'll leave him out of the discussion altogether because they told him where to look. But along with Herschel, all of these women, I'm giving you encapsulated views of what they did. If you look them up and read their life histories, there's a lot more to all of them than I can tell you. And several of them are probably worth a talk almost entirely by themselves. They have many more accomplishments in science and math than I can describe in a short lecture like this. Now, while the English don't really have a big problem with smart women either the way the French do, because we just saw that Herschel and Somerville got elected to the Royal Society, they had a big problem with non-Anglican women. And that's where Mary Anning gets into trouble. She was a very well-known paleontologist, one of the most important discoverers of fossils in the early years of the 19th century. Basically, nobody remembered who she was until 2010, when all of a sudden the Royal Society said she was one of the 10 most important women in English science history. She discovered several different fossils, the first ichthyosaurs, the first complete plesiosaurs, and a whole raft of other fossils, almost none of which she got credit for. While the members of the Geological Society of London privately would talk to her and acknowledge her publicly, they would not, and many of them took credit for many of the discoveries that she made. And she was basically poor most of her life. And she sold seashells by the seashore to make a living. And in fact, if you've heard the old tongue twisters, she sells seashells by the seashore, she is the one it was written for. So she's the original woman who sold seashells by the seashore. And it's not famous for it, but it's about all that's left to her these days. Eventually, many years after she was gone, the British decided, yeah, we shouldn't have picked on her. Almost certainly, if she had been Anglican, she would have been recognized in a manner similar to Herschel and Somerville. But it was still a big deal in the early 1800s in England to be Anglican. And this is, of course, one of the big reasons why the people came to America for what they called religious freedom, which was not religious freedom the way we think of it. It was the freedom to tell you to be some other religion than Anglican, but it was the same kind of thing. So unfortunately, she did not conclude as happily as the other stories. Now, Augusta King, I've hidden a whole story in here by saying that after a complicated childhood, Mary Somerville, we just saw a few moments ago, introduced her to Babbage. Well, she's the only legitimate child of Lord Byron, the famous poet, and his wife. And when she was about 8 years old, Byron skipped out on both of them and went to the continent with his new girlfriend, wife, and abandoned them. And so his wife, Anna Isabella, decided that Byron was insane. And she decided that the reason he was insane was poetry. Poetry drives you insane. And so, rather than allow her daughter to be brought up with the usual female education in Europe, which was literature, language, poetry, art, then my kid is not going to learn any of that damn poetry that drives people nuts. My kid's going to learn math and science. And so it was a very strange education for a girl in Europe at that time. But her mother saw to it that she had a heavy education in math and science, and so, of course, Mary Somerville was the perfect tutor for that kind of thing. I spent quite a bit of time with her. Introduced her to Babbage, who, as you may remember, created the first mechanical sort of digital computers. He created two, and I don't remember what they were both called. I probably have it up here somewhere on my slide. The difference engine, which he actually built, and the analytical engine, which he didn't. So, Ada, who did have an education in languages, because she was really smart, translated an article from Italian into English on the analytical engine, which Babbage had not built. Her translator's notes were about 3 times longer than the paper she was translating. And so she wrote like whole extra chapters, basically, that the Italian guy left out. And one of the things she did was she wrote down an algorithm, a collection of instructions. If Babbage had built the analytical engine, had you done these things with the engine, you would be able to generate the sequence of what are called Bernoulli numbers. And Bernoulli numbers are not a simple sequence like the Fibonacci numbers or something else that you can just write down. They have to be derived from a Taylor series expansion, which means that she knew how to do the derivation from a Taylor series expansion and knew how to write that into an algorithm to give to the analytical engine. And we now know from our own modern studies, had the engine been built, her algorithm would have done what she said it would do. It will reproduce the Bernoulli numbers. So she gets credit for being the first person to write a computer algorithm and the first person to write a computer program, male or female. And last Saturday in the 100-inch telescope, I heard one of the guests insist that she was, because of this, she was the world's first systems engineer. Now, whether that sounds like a bit of a stretch to me, you might argue that she was a systems programmer, but that's a bit of a stretch too. But it certainly, she wrote the first algorithm for a computer. That's no doubt about that. And it would have worked. So it counts both as an algorithm and as a program. So she's the world's first computer programmer, and if you may remember some years ago, the Defense Department invented their own new computer language called Ada, which they named after her. And one of my colleagues at JPL named his daughter after her too. So. Now Maria Mitchell, she is the first professional woman astronomer in the United States. Raised by a Quaker family, and they believed in lots of education. And so she discovered a comet. Well, now these days, discovering a comet will get you mentioned, but it's not quite as big a deal as it was back in the 1800s. And especially for a woman to discover a comet, because women never did this kind of thing, right? So she got a gold medal from the King of Denmark and became internationally famous for discovering this comet. And as a result of her newfound international fame, she was hired on as a professor of astronomy at Vassar College, which made her the first person to get paid professionally as an astronomer in the United States. And she established her observatory. There she is here with her first class around 1865. And of course she had no formal schooling like most women at this time. She taught herself, had been tutored, or whatever. But perhaps more importantly, in the modern sense of things, she is one of the early women that I can find a record for to argue about being paid less than men. And she discovered that faculty members at Vassar, male faculty members junior to her, were being paid more than she was. And so she took this to the university leadership, and all of her correspondence on that is in the archives of Vassar College. You find it in their library. You can go through it. So the back and forth letters between her and the management. She had the advantage that other women didn't have. She was famous. She's actually internationally famous. So when she threatened to leave, that attracted attention. They wanted her to stay at the college because she was famous. And so there's a back and forth about, well, you live on the campus, we give you, room. But yeah, but that would cost this much, and they get this much, and the differences. And so they went back and forth, and eventually they settled on a deal where she got more money. So if you're interested in championing equal pay for women for doing the same job as a man, Maria Mitchell, as far as I can tell, is the first woman in this country to do so successfully. At least we have a good record of her correspondence. We know what she did and how she did it. And a whole bunch of other things. First female professional astronomer in the country. The Vassar College things were always pretty much the same things, all appointed at the same time. And first woman elected as a fellow of the AAAS and the Academy of Arts and Sciences. So she made quite a splash, and you want to remember because her name is going to show up again later on. Sarah Frances Whiting was a professor of physics at Wellesley College. She, Edward Pickering, we're going to see his name again a lot with the Harvard computers. Edward Pickering was one of the few guys around at the time who seemed not to mind very much having women work with him. So all the other men were like, nah, come on, women can be my secretary, but they can be scientists. But Pickering wasn't bothered by this. And so he let Frances Whiting audit classes of his at Harvard, and he brought her to his laboratory where she studied spectroscopy. And Pickering had established the first experimental physics laboratory in the country at Harvard University. And she established the second one with his help, and the first one for women at Wellesley College. And many of the women who show up as Harvard computers with Pickering later on learned from Sarah Whiting at Vassar. And this is a passage that Annie Cannon, was a student, wrote in her obituary for Sarah Whiting in 1927. She says, an especially exciting moment came when the Boston morning papers reported the discovery of the Röntgen or X-rays in 1895. The advanced students in physics of those days will always remember the zeal with which Miss Whiting immediately set up an old Crookes tube and the delight when she actually obtained some of the very first photographs taken in this country of coins within a purse and bones within the flesh. So she wasn't just a physics teacher who set up the first physics lab for women and the second physics lab in the country, but she had her eye on physics research, what was going on in the world, and kept herself at the forefront. So if there was some new development somewhere, she brought that into her physics lab right away and made sure her students were aware of it, so they weren't getting old-fashioned stuff, they were getting the latest. And she is very influential in establishing physics education for women in this country. Now we come to the subject of Dava Sobel's book, the Harvard Computers, the women who worked with Pickering at Harvard College Observatory. Williamina Fleming, up here, came from Scotland. Her and her husband were not particularly rich. I mean, they were ordinary, lower middle class, upper poor class. And they got here from Scotland, and her husband ditched her and ran off, who knows where he went. And she had to take care of herself, so she hired on as a housekeeper and worked for Edward Pickering as his housekeeper. Pickering, meanwhile, was taking on a great deal of work to do the Henry Draper catalog of stellar spectra, and the men who worked for him were not performing up to snuff. And in a snit one day, he yelled at them that they were so bad his housekeeper could do a better job, went home, got his housekeeper, brought her and said, okay, here's what you need to do. And she did it for an hour or so, and then he fired everybody and told her, okay, it's you take over. And so Williamina Fleming took over. She's the one who discovered the Horsehead Nebula, almost invisible on one of the plates at the Harvard College Observatory. But she proceeded to hire only women to do all the computer work. Pickering had no problem with this, partly because he had no problem with women working as long as they could do the job, and partly because in those days you could pay women less than you paid men for doing the same job, despite Maria Mitchell's success at Vassar. It was still the case that he could pay women less. So he saved money, he got the work done, it was really great for him. And of course, all these other women who had employment, Antonia Mowry, Henrietta Leavitt, Annie Cannon, Cecilia Payne was a Harvard computer for a while. And perhaps the two most famous of the lot are Annie Cannon and Henrietta Leavitt, photographed here in 1913. Now, Leavitt is the one who made one of the most important discoveries in history of cosmology and astrophysics. She earned her degree at what was then called the Society for the Collegiate Education of Women, which is now Radcliffe College in 1892, joined the Harvard Computers. She was studying what were called cluster variables at the time, which are now called Cepheid variable stars, in Magellanic clouds. And she noticed something about them that was peculiar, and she mentions it in a 1908 paper, saying it looked like they varied in a consistent way with their brightness. There was some kind of relationship between the brightness and the period with which they varied. But then she wrote this out more completely later on in 1912. Her discovery, in my opinion at least, is most fundamental in cosmology, just like the discovery of the CMB. They're both very fundamental in that they're going to be part of the astronomy business forever. Edwin Hubble suggested she should get a Nobel Prize for this, and Matthias Leffler, whose name I believe I will mention again in a little while, as a mathematician from Sweden, decided he would nominate Henrietta Leavitt, and when he came to look her up in 1924, only to discover that she had already passed away in 1921. You can't nominate posthumously for the Nobel Prize, but it probably was a Nobel-worthy achievement because it's enormously important. And this is basically what she discovered. She mentioned that it looked like this in 1908, and then these plots are from her 1912 paper when she lays it out. Along this axis, well, this is a linear plot. This is what you'd expect in a normal graph. This is the period with which the brightness of the star varies in days. So this is a star that has a period of 80 days. So between peak brightnesses, it's 80 days. Here's one that's 40 and 20. And this is the apparent magnitude. This is the logarithm of the period and the linear scale for the apparent magnitude. So a curve like this on a linear plot, which, as you can see, is pretty noisy. The data's kind of ratty. But on a logarithmic plot, it's going to make a straight line. And so if you use the logarithm as your variable, then you have a linear equation from algebra, and it's much easier to deal with than something that looks like this. But this part, this is the bottom line here, is the part that kind of gets skipped over in most discussions. Everybody knows that we use Henrietta Leavitt's discovery of the period luminosity relationship for Cepheid variables to derive cosmological distance scales, and everybody says that. But she did not know how far away these stars were. So while she knew clearly from this plot there is a relationship, you can't calibrate it to a distance from these data because you don't know how far away it is. So all you know is there's a relationship. You need a distance. And that's what Einar Hertzsprung, the Hertzsprung-Russell diagram, he did that in 1913. As soon as he heard about this, he ran off. But he did what's called statistical and secular parallax, which is not trigonometric parallax the way you think of it. It's kind of like the vanishing cluster method for globular clusters. You look in the direction the Earth is moving, and you either look at the proper motion of the stars that you can see, and then you look at, and I forget what else you're looking at, radial velocity. Either looking at the radial velocity or the proper motion, and taking a projection along the velocity vector of the Earth, and you're getting a statistically average parallax for the stars. It's not as precise as a real parallax would be, so there's some slop in statistical noise and that kind of thing. But you can do it. And he did that to calibrate this to a distance scale. So the calibration is statistical. It's just not, and we'll run into that problem later on. It's not a solid calibration yet.
Looks like the fit is not the same on the two curves. On the left, on the linear curve, this the bottom one, the second to the last point is below the curve. Over on the log plot, the second to the last one is above the curve. So I guess she used a slightly different fit on the two?
She probably did. A great deal of work has been done on this since then.
Yeah.
And so, yeah, nobody uses these relationships.
Yeah, I'm just surprised that it looks like she used a different fit.
Yeah, and I don't know why that would be.
The other points seem to be pretty good.
So you're looking at these two, yeah, I don't know. It's probable. I don't know if what kind of a fit she did with this. She might have eyeballed.
Yeah.
Because that's typical what you do with a log or with an exponential curve like this. People just kind of eyeball it. And then when you get on the line, then you can do a least squares fit or something.
I'm kind of surprised she didn't work back
Yeah.
on that.
So probably did. That's my guess. I don't actually know.
Yeah.
I have a copy of the paper, and you can download it from the NASA ADS and actually read
quite
it.
surprised to see that.
You're the first person to notice it, actually. I've given this talk many times, and you're the first guy.
Another question is, what are the two curves?
What are the two? These are allegedly fits to the data. So they are statistical fits, like the least squares or something. So this is the best fit line.
No, but I mean, why do we have two curves?
This is the star at its minimum brightness, and this is the star at its maximum brightness.
Okay.
This is a variable star.
Yeah.
So when it's brightest and when it's dimmest, those are the easiest points to pick out in cycle of the star getting brighter and dimmer halfway. It's kind of like, is that halfway? I don't know. But you can tell when you get to the bottom and the top without much trouble. So that's what that is. And that's where she sees, well, there's clearly a relationship. And she knew if she knew the distance, she'd get the absolute magnitude. So Hertzsprung took care of that. And so the result is that the way we do this today is we have an equation that looks like this, and where the log of the period is used to your linear. But of course, if you just skip this thing right here, just consider this to be your x-axis variable. This is the slope-intercept form for the equation of a straight line. So you got the slope and the intercept. This is stuck in here as an extra parameter for fitting, because the slope tells you what the angle of the line is. This intercept tells you where up here you are, and by sticking this in as an additive to the log, you have a horizontal degree of freedom when you fit. So if you're doing it like a least squares fit to the data, you want that extra degree of freedom to find the best fit line, so you stick this in as a fitting parameter. You don't really need to do it if you're straight algebra, you can skip it. And that's what we do today. So originally it was one equation, then it became two. Now there are like 5 or 6 or 10 equations, because modern astronomers have built in metallicity dependence, whether it's a population 1 or 2 star, and a whole bunch of other things, F3, whatever it is. I can't remember the population. Yeah, a little star or big star. So there's a whole bunch of different variables that astronomers put in there now. So there's like a little collection of equations like this, where originally there would have just been one. So it has turned into a huge thing for getting galactic distances. And then eventually, when Hubble and Shapley mapped out the galaxy and the universe at Mount Wilson Observatory, they were using this and doing it wrong, because they didn't realize there were 2 different classes of Cepheids. And so Walter Baade split this equation into 2, and then now it's been split into 4, 5, or 6. But he made a major repair to cosmology just by splitting it in half. Now Annie Cannon, she ran into this interesting problem where she got her BA in physics and couldn't really get a job. And so she had money, she toured around Europe, and she got scarlet fever or something like that that affected her hearing, so she was almost deaf. Henrietta Leavitt was deaf. Cannon was almost deaf. And then she got her MA in physics, and she was working with Sarah Whiting, and she got her master's degree in physics and still couldn't get a job, right? Because nobody hired women to do physics. And so she went back to Sarah Whiting, like, what do I do? How do I get a job? You know people, what do I do? She said, well, talk to Pickering. He's got a lot of women working for him. And so she went to talk to Pickering and Fleming, and they hired her. And so she's the one who put together the final form of the Harvard spectral classification system that we use today. And in so doing, she examined with a magnifying glass, because the spectra on the little glass spectra, just little tiny things. So you had a magnifying glass look at these little spectra. And she got to where she could classify 3 stars per minute. And she classified about 500,000 individual stars herself with a magnifying glass and glass photographic plates. Nobody ever did more than that before, and nobody will ever do that many again, because computers do it now, right? Electronic computers, not female computers or human computers, but electronic computers. And so that's a record that will probably stand forever. Same as the record number of stars that Clyde Tombaugh looked at in order to discover Pluto, like 8 million stars or something. And nobody's going to do that again either. Along the way, she also found about 300 variable stars, a few novae spectra. This is kind of interesting because she was the first woman to receive an honorary doctorate from Oxford University in 1925. Oxford University, as we will see, did not grant any degrees to a woman at that time, until I think 1926, actually. So there were women who passed all of the degree examinations, and if they were men, they would have simply been handed a degree, but instead they were handed a piece of paper that said they passed the test, but they were not given degrees. And that's one of the reasons Cecilia Payne came to the United States, because that's what they did to her. And so it's curious that an American would be the first woman to get an honorary doctorate from Oxford. There were plenty of, Somerville, there's a college at Oxford named after her, Somerville College. They could have, any number of British women, but no, they picked an American. So I don't know what was going on at Oxford at that time. They were dollar-owned women. So this is the spectral classification scheme that Annie Cannon finally came up with. And now, of course, there's lots of sub-classifications that have been added to it. It's been modified, but basically this is what we're looking at. And here are examples of what the spectra look like. So Father Angelo Secchi is the guy who came up with the first scheme to do this, and he's the guy who actually also invented the Secchi disk for determining how turbid water is. And I've been to Lake Tahoe, and we use a Secchi disk that you lower it, and you look, and when it disappears, you measure how far down you send it, and that tells you how opaque the water is. So you measure water clarity using a Secchi disk. So while he wasn't inventing ways to measure water clarity, he was categorizing stellar spectra. And the first woman to get the assignment to turn that into something was Antonia Maury, who, as it turns out, her uncle, U.S. Navy Commodore Maury, was a good friend of Angelo Secchi's. I think it's just one of those historical weirdnesses, coincidences that happen now and then. But Williamina Fleming and Pickering didn't really like Maury's scheme. Maury did not like that they did not like her scheme, so she left. And then later on she came back, because I guess she couldn't get a job. And so she came back. But so Fleming tried it, and then they finally gave the job to Cannon, and she's the one who came up with it. And I'll just point out that M stars, the dwarf stars especially, are a huge majority of stars. And so when you get to G class, where the sun is only about 3%, the result of this is that the sun is actually bigger than about 95% of the stars in the galaxy. And everybody will tell you the sun's an ordinary star, it's an average star. Well, it's not average, it's bigger than 95% of the stars around it. So you can feel better about not orbiting some average ordinary star. You're orbiting a star that's bigger than 95% of the stars around. It's pretty hefty, right? And of course it's still classified as a yellow dwarf because it's a main sequence star. So only in astronomy can you be bigger than 95% of the things around you and still be a dwarf. So that means big stars are like really big. And then we come to Cecilia Payne, who later became famous with the name Cecilia Payne Gaposchkin. So what she did, and just to give you some context, let me back up one thing. If you look at these, look at the lines of the spectra, astronomers learned in the mid-1800s how to do surprisingly precise observations of the stellar spectrum. But they did not know why stars had spectra. They could measure them, but they didn't really know what they meant. But by working in the laboratory, they could figure out that these lines, there are patterns hidden in these lines that tell you what the elements are. So they were able to do that. And they had laboratory classification, so they could do that. They could use the spectra to identify specific elements. They also knew how to look at the difference in lines, like here's a line that's strong and gets weak, and here's a line that's weak and gets stronger. There are variations in the lines that are temperature dependent. That they could also calibrate in a laboratory, so they could get temperatures by looking at the lines. But while they could identify the elements, they had no idea how to turn that into an abundance, how much of that element is there. So they made a very simple and very wrong assumption. The more lines there are, the more of it there must be. And so if you look at the sun spectrum around the green has lots of iron lines in it. And you ought to know about the sun spectrum.
Seen it before.
Never seen it before. And it has lots of iron lines. So everybody assumed that the sun was mostly made of iron. and heavy elements, because there are lots of metal lines, and there's only one hydrogen line, so like no hydrogen in the sun, practically none. Okay, two. What do I know about radio astronomy? I didn't do stellar spectroscopy.
Spent most of my life in the infrared, so hey.
And so the assumption was always that stars were made out of heavy elements. That's why, if you've ever heard of Campbell's hydrogen star, which was discovered by Campbell in the late 1800s, at a time when stars were assumed to not have any hydrogen in them, or not much, that star has a hydrogen alpha envelope around it. It's very prominent, very obvious. And so it was very strange. It was the only hydrogen star anybody had ever seen. And so they made a point of calling it the hydrogen star. And that's why it has that name, because in those days the assumption was all stars are made of iron. And so it's really weird to find one with hydrogen. And now, of course, we would say if you find that much iron, that would be really weird to say. Right. Well, nobody knew how to do any of this stuff, but once quantum mechanics came along, and de Broglie gave us his model for the atom, and Bohr was coming up with his original quantum mechanics, Meghnad Saha in India was looking at this Bohr model for the atom, the electrons going around a nucleus, and calculated ionization states. What if you kick an electron off the atom? How does that change the spectrum? And Cecilia was the first one to apply that to a stellar atmosphere. So when she did, she discovered that the reason there were all those iron lines is because iron has lots of electrons, and you could knock lots of them off and get lots of ionization states. That's why there were lots of lines. So when she turned that into an abundance, she realized, oh, the stars are almost entirely hydrogen and helium and nothing else. All those iron lines are just ionization states of a very small population. That was considered to be impossible at the time. And her thesis advisor, primary advisor, Henry Russell, first he didn't want to give her a PhD for it because he thought it just can't be right. This is obviously wrong. You must have made a mistake somewhere. Okay, put that in your thesis and I'll give you a PhD for it. So she kind of did. Didn't mention in her thesis that maybe it's wrong, I don't know, but you know, this is what I get. And so they gave her a PhD for it, but they all thought she was nuts. And then about 5, 6 years later, they all decided, actually she was right. And so Henry Norris Russell wrote a paper in 1929 deriving the same results as Payne with a slightly different method. And if you've seen Neil deGrasse Tyson's New Cosmos series, he makes a point of saying that Russell, to his credits Payne as the discoverer. I'm not convinced of that because I've read Russell's paper, and you really have to dig through it to find that little part where he mentions, oh, by the way, Cecilia Payne did something like this for a PhD thesis. Nobody would read that part of the paper probably. So, in fact, you will find a lot of people, and I was one of them for many years, who thought that Russell made that discovery because of his 1929 paper. And it's only after you really dig into the history you discover that actually it was Cecilia Payne who made the discovery, not Russell. So you'll still run into people who think it was Russell. So this discovery that stars are made out of mostly hydrogen and helium is obviously the discovery you need to make if you're going to understand stellar physics at any level, nuclear fusion, all that good stuff. Everything comes from your realization that stars are made of hydrogen. Until you come to that realization, you'll never have a clue what stellar physics really is. Everything will be wrong. So it's generally referred to as the most brilliant PhD thesis in all of astrophysics, which may very well be true. And by the way, she came to the U.S. in, was it 1925? I think, no, she came 23. She came to the United States in 1923 because Cambridge also would not grant degrees. Oxford and Cambridge wouldn't give degrees to women, and she didn't feel like passing all the exams and not getting a degree. So she came to the U.S. Well, of course, you've probably all heard of Marie Curie and her daughter, Irene. Marie shared the Nobel Prize in Physics with her husband. got a Nobel Prize for herself, and Yeren shared a Nobel Prize with her husband. And so she's got two. So the Curie family's got 5 Nobel Prizes, which is the most Nobel-heavy family in history. Marie was not nominated by anyone for the 1903 prize. Only Pierre was nominated. And it was Mittag Leffler who told Pierre, you're going to get the prize, but not Marie, only you, because she was not nominated. And so he went to the committee, or he wrote letters to the committee. Whatever he said, I don't know, but the upshot of when they gave the prize, they gave it to both of them instead of just him. So either he threatened not to take it, or he convinced them that his wife had done the lion's share of the work and deserved credit for it. And so she got this prize because her husband went to bat for her with the committee. This prize she received for Nobel Prize in Chemistry for work very similar to what she'd done in 1903. And this became an issue in 1911 when she was nominated for membership in the French Academy of Sciences. And the very nasty fight that resulted from that resulted in at least one higher up in the Academy resigning his position, a couple of them being fired, a few private detective investigations, and a whole lot of really nasty stuff. And in the end, the French Academy of Sciences refused to give her a membership, despite having 2 Nobel Prizes, one in physics and one in chemistry. The primary reason they gave was that she was Polish, and they didn't want to have a Pole as a member of the Academy of Sciences. She was born in Poland. The second most important reason they gave was that she was Jewish. And then they mentioned that she was also a woman. And in fact, no woman was permitted to be a member of the committee until 1965, when one of Marie Curie's students was elected to the committee. Otherwise, I think it was 65. Otherwise, it didn't. So her membership in the committee was a nasty fight. You could write a book about all the stuff that went on there. And of course, her daughter shared the Nobel Prize with her husband. They had achieved the alchemist's dream. They had actually transmuted one element into another. Now, back in Newton's day, they all thought if you just mix the right stuff together, you change lead into gold. But it turns out it doesn't work. But they were able to do that kind of thing by pounding atomic nuclei with particles until they changed to a new element. But of course, it happens in very small quantities. Changing a pound of lead into a pound of gold is still hard work, no matter how you do it. Emmy Nether, she always used the name Emmy, and her name is cut off at the top of the slide. But that's Emily was her given name, or Emily, but Emmy is the name she always used. Probably one of the most important mathematicians of the 19th and 20th century. Certainly Weyl and Einstein, and she worked with Hilbert. He must have had the same thing to say, that she was the most important woman mathematician ever. From physics, the thing that stands out is Nether's theorem in 1915. And the simplest English I can translate it into, which is not really all that simple, but it's math and there's a limit to what you can do, is that any differentiable symmetry of the action of any physical system has a corresponding conservation law. The action of a system is an integral of the Lagrangian, time integral. So you have to know something about Newtonian mechanics and Lagrangian dynamics in order to follow all this. But the bottom line is that if you take a conservation law, like conservation of energy, conservation of momentum, things which you derive from experiment, you do a sufficiently large number of experiments and you say, okay, I see this happening, and it looks like a law. And you keep doing it, when it happens forever, you say, okay, this is a law. It turns out you can derive all of that from pure mathematics without doing an experiment at all. You can derive the fact that these quantities have to be conserved. And that is what Nether's theorem does for you. So you can take Nether's theorem and apply it in a quantum mechanical or field theory or string theory. You can do any of that, and as long as it is a system that can be described with a Lagrangian, then this applies. And so you can derive conservation laws in quantum field theory and all kinds of advanced stuff if you're a Stephen Hawking fan. So, very fundamental in mathematical physics. Probably it's the most important single theorem in all of mathematical physics, really. But she had all kinds of other accomplishments in mathematics, where she studied algebras and rings and fields and group theory. She spent a lot of time working with Hilbert, and she had the same kind of problem. She tried to get a degree from several different places that wouldn't let her in, and finally got a degree at I think it was Erlangen, University of Erlangen, and then when she Hilbert brought her to the Göttingen, that had the biggest math center in Germany and Europe at the time, but the faculty of philosophy at the university complained about having a woman on the faculty, and so that she couldn't be paid. She had to lecture under Hilbert's name, so all of the lectures that she gave were in the syllabus with Hilbert instead of her. And she couldn't get paid, but she finally, in 1919, I think it was, passed her habilitation, which in Germany, you know, you can't teach until you do what's called a habilitation, which is like a second PhD, in order to qualify you for teaching. It's quite a complicated affair they have. And it's still the case. In most of Europe and in Germany, you have to do a habilitation thesis before you can teach. Yeah.
What was Einstein's relationship with her? Did he like working with her?
I don't think Einstein worked with her directly, but her theorem and conservation laws are critical to general relativity, and he knew that, and he was familiar with her mathematics because he studied that stuff. So he recognized that her advances, especially in Nether's theorem, were critical in mathematical physics, and that's, I don't know if he knew her personally, or he must have met her at some of the conferences, because he was at all those. Hilbert, she worked with on a regular basis at Göttingen, and Hilbert is like the greatest mathematician, the mathematician's mathematician of the 20th century. But she eventually, after passing her habilitation, was allowed to become what's called a Privatdozent in German. Private docent. It means that the university will let you teach, but the students pay you directly, and you have to negotiate with them how much they pay you. And that's Privatdozent is the German word. And it was typical for entering the faculty of a German university. That's the position you get. You had to have a PhD to get it. They would give you a room to teach in, but you had to make your own arrangements with whatever students and whatever price you wanted to charge. It was entirely up to you, and they did not pay you, the students did. So Elisa Meitner is famous for not getting the Nobel Prize, because Otto Hahn, he discovered in his laboratory experiments that when you collided uranium and neutrons, he got barium. So where did the barium come from? That's kind of crazy. And he didn't really understand it. Well, Lisa Meitner was working with him, and they were pretty good friends. But in 1933, Meitner decided being in Germany was a bad idea for a Jewish woman, so she went to Sweden, and Otto Hahn stayed behind. And Meitner, while she was in Sweden, she figured out what had happened. Hahn's experiment told him, what you're getting is nuclear fission, the breakup of the nucleus. And so Hahn and Fritz Strassmann published their experimental work. And at the same time, Meitner and her nephew, I think, Frisch, published their physical explanation. They published their papers together at the same time. And when the Nobel Committee handed out their prize, they gave the 1944 Nobel Prize in Chemistry to Hahn. And they did not mention Meitner, who's the one who told Hahn what he had discovered, so he didn't know. And they didn't even mention Strassmann, who did the experiment with Hahn. So if you were going to give the Nobel Prize for the experiment, you'd think that both Hahn and Strassmann would get it, but only Hahn got it. And then nobody really understands why Strassmann or Meitner were not mentioned. But Hahn got the prize and somehow managed to get a hold of the metal, which he melted down and hid because the Germans were stealing gold from everybody. The Nazis were still in power at the time, were stealing gold from everybody, and he hid it. And then when he got out of Germany after World War II, they restruck a new Nobel medal out of the gold that was the old medal that he had managed to hide from the Nazis somehow. That was quite an adventure, too. So one thing you can tell is that Maria Geppert-Meyer got the second Nobel Prize in physics. So for a long time, I argued that the only way you get a Nobel Prize in physics would be named Mary, because there's Marie and Maria. This year, you know, that changed. But first off, in this photograph, now probably most of the people in this room know what this device of ancient witchcraft is. You know, you never see them anymore. They're in old dusty drawers. Young people have no idea what they are. But they were actually quite useful. I have a small collection of them, and you probably do too. So she, with Hans Jensen, created new models for atomic nuclei, looking at the dynamics of individual particles, where models of nuclei before that, it's kind of the shape of the nuclei, but it kind of ignored the things that make up the nuclei. Is it round, is it a little oblate, whatever. And she started looking, well, what if we look at the stuff that's made out of the nucleus, and then we can put them in energy shells the way electrons go in shells around them, and build a more complicated model of the nucleus to understand how atomic and atomic nuclear physics actually work. And so she received the Nobel Prize in Physics in 1963. And she was also working on the Manhattan Project doing isotope separation and the like. But her big deal was nuclear physics, which is what she got her Nobel Prize for. So this is kind of doubly interesting. Dorothy Crowfoot Hodgkin got her prize for really introducing X-ray diffraction techniques to biochemical molecules. X-ray crystallography, as you can tell from the name, came from the analysis of crystals. Well, she discovered how to take not so crystalline biological molecules and get three-dimensional models from X-ray diffraction of what they look like. It's very important in molecular biology to discovering how molecules interact with each other, why do chemical bonds work the way they do. You need to know the shape of the molecule, and you can get it from this. And she was the third woman to receive the Nobel Prize in Chemistry. But most interesting, perhaps, aside from her own achievements, was one of her students, Margaret Roberts, who earned her second-class honors degree working in X-ray crystallography with Hodgkin, and she did a 3D modeling of a complicated antibiotic with amino acids in linear chains that stick out in various directions. It's quite a complicated job. And she later got married and became known as Margaret Thatcher, who was the Prime Minister of the United Kingdom for many years. The longest serving woman Prime Minister, and at the time I wrote this talk, she was the only woman. Now they have another woman Prime Minister, so she's not the only one anymore. What was the longest serving? And so in case you didn't know it, Margaret Thatcher, famous for being Prime Minister of England, had an honors degree in chemistry from Oxford University and was an expert in X-ray crystallography. So every once in a while, scientists actually get into positions where it's good to know some science. That doesn't happen in this country, but yeah, we can always hope. So Vera Rubin, she graduated from Vassar College in 1948 and applied to Princeton, but Princeton did not accept women into their graduate astronomy program until 1975. And the reason is not because Princeton suddenly became enlightened, but if you do a little legal research, I went looking to try to find the reason. in that same year, Congress passed federal anti-discrimination laws that made it very difficult to deny women entry to your academic programs in the university, and that's almost certainly why Princeton chose 1975 to let women into their graduate astronomy program, because the federal law had changed around and they kind of didn't have much choice. So there's no telling whether Princeton even today would let women into their graduate program if the federal law had not intervened. So she got her PhD from Georgetown. I always thought if she drove by Princeton, she'd probably be doing this as she did. So her PhD thesis was on galaxy clusters, which is kind of peculiar because this is usually cited as the first proof using dynamics that galaxies actually cluster. So what appear to be galaxy clusters on the sky is not just some accidental overdensity, it's a dynamic entity. But if you look at the literature, it's pretty obvious that astronomers knew that way back when. Fritz Zwicky's first papers on what we now call dark matter had to do with the dynamics of galaxy clusters and the assumption that they're gravitationally bound. So I'm not altogether sure what to make of the description of her PhD thesis. But she was unhappy because nobody paid any attention to it or told her that your thesis is crazy. It's just like Cecilia Payne. They told her you're nuts. The thesis is all wrong. So depressed, she went off, I'll just do something ordinary and study the rotation of galaxies. So she got in touch with Kent Ford, and he built an instrument, and they started doing spectroscopy and studying the rotation curves of galaxies, and discovered that they rotate wrong, right? And so the modern apparition of dark matter comes when she points out, well, these rotation curves are flat when they should fall off. They're non-Keplerian. They don't obey Kepler's law. And of course, she ran into more than again, it's like, hey, you're nuts. No, this, she pulled her hair out. I didn't know what to do because everybody keeps telling her she's nuts. And then after a couple of years, she's like, yeah, you're not so nuts after all. And so now, Fritz Zwicky suggested dark matter, Jan Oort suggested dark matter, and people kind of, yeah, maybe, forget it. It was Vera Rubin. She wasn't the first, but she's the one who made it stick. She proved that the galaxies weren't rotating right, and then she pounded the table. I'm tired of people telling me I'm nuts. If you think I'm wrong, prove it. You know, they all scratch their heads, and guess what? Maybe you're right. And so,
what was that lady's name?
What was that?
Who is that again?
Vera Rubin. Her name is cut off way up at the top, but here's her name above.
Oh, yes.
Yeah, I never met her, but a lot of people that I know did. She passed away in 2016. Now, I'm also going to mention Henrietta Slope, because if you remember late last year, the LIGO project people, after they had discovered gravitational waves from colliding black holes, but we all knew they were black holes already anyway, we didn't need gravitational waves. But discovering gravitational waves directly is a nice thing. If you believe in gravitational waves, you want to prove them. But the real excitement was when you discover gravitational waves from colliding neutron stars, and then discover the explosion created by the neutron stars, which is this thing here. And it was made using the 1-meter Henrietta Slope telescope at Las Campanas Observatory, and there's Henrietta. So, Henrietta, as it turns out, did quite a bit of work. She joined Carnegie Observatories after World War II, but she worked with Walter Baade. Her father, like her, the two of them were both quite talented at manipulating stocks on the stock market. And so she is a peculiarity in that she was a fairly rich astronomer. Because astronomers don't get rich, right? Nobody makes a hell of a lot of money doing astronomy, you already know that. But she didn't make a lot of money. She made money because she got paid, but she didn't make her millions in astronomy. She did it on the stock market, and her father gave her quite a bit of money. She was a contemporary of Cecilia Payne Gaposchkin, But she donated $650,000 to Carnegie Observatories specifically to develop a southern hemisphere astronomy facility. And it's the birth of Las Campanas Observatories is really Henrietta Swope's bequest to Carnegie. And the 1 meter Henrietta Swope telescope is an F7 Ritchie-Chrétien with a 3-degree flat field. And it was this telescope and a team of Carnegie astronomers that discovered, there's the telescope there, sir, that discovered what they call the kilonova created by the collision of neutron star. And this actually gives us a linguistic problem, right? Because we have nova, supernova, hypernova, and kilonova. We're running out of prefixes, right? So what's the next? It's going to be a meganova? What's the next thing? They're going to find something, and they're going to need to put a prefix in front of nova, and they're running short. You know?
Bigly nova.
Yeah. At some point, they're going to have to invent some new word. Now, Grace Hopper, as you can tell from this picture, is the wrong woman to get in the way of. She told the story of going to some conference in her civilian clothing, and it was a Navy facility, and she didn't like the way the Navy guy at the front desk greeted her. So she went back to her hotel room and put on her Rear Admiral's uniform and came back, and basically when he snapped to attention, she just kind of said, "Do you remember me? I walked in here a while ago." Guess what? That was a mistake. And she used to carry fiber optic strands around with her that were labeled for the time delay they would give. And when somebody asked her, how long is a nanosecond? And she said, well, I just whipped out my 1 foot and said, it's this long, as a prompt. So she's the one who invented the compiler for computers. So if you've ever used a compiled language, she's the one who invented compilers.
COBOL.
And she invented it and nobody paid attention to her. However, we heard this before. And so she got mad because everybody told her nobody's useless. So you invented a compiler. Who cares? Nobody's going to use it. Why would we? So she also had to invent the first compiler languages because nobody would do it. So she did it. So she invented the first compiler, invented the first compiler languages, and finally, after beating enough people over the head long enough, was able to prove that compilers were worth having. And then, because it's from there, the rest is history, as they say. This whole modern era of computers and compiled languages and Fortran and C and all that stuff owes its origin to her. She had her PhD, of course, in mathematics. She was in the Navy starting from 1943. She retired in 1966, was recalled to active duty in 1967, retired in 1971 for the second time, was recalled to active duty in 1972, retired for the third time in 1986. It took an act of Congress to permit her to remain on duty beyond mandatory retirement age. And when she finally retired for the last time, she was the oldest serving commissioned officer in the Navy at nearly 80. She was 79 years and 8 months old and was a fixture in the U.S. Navy. She earned the Presidential Medal of Freedom in 2016 and several other medals just because of her long naval service. But there's something else that she did. She was not the first to use the word debugging or bug with respect to computers, but she was the first one to make it popular, and she was the first one to actually catch the bug. And so, and Moth flew into the relays of one of their old electromechanical computers. They recovered the corpse of the moth, taped it to the computer logbook. That logbook and the moth corpse, which is here, are in the Smithsonian collection today, and so you can go.
First bug.
That's right. You can go and look at the first computer bug if you want to. There's its corpse. And so there, the proof that there was a real bug, you had to, it's in the military, you've got to justify calling it a bug, right? So there it is. There's a bug. And of course, because of her long and distinguished service, DDG-70 is named USS Hopper after her, one of only 2 ships named for women that were actually in the Navy. And so that brings us to 2018. Prior to this year, only 2 women had a Nobel Prize in Physics, but this year, a share of the Nobel Prize went to Donna Strickland at school is she? I forget what school she's at now. She's in Waterloo, University of Waterloo, Canada. I believe she was an associate professor at the time this award was announced, and the university fairly quickly promoted her to professor. That's because if you look on her Wikipedia page now, she's a professor, and as far as I know, she was an associate professor. Prior to winning the Nobel Prize, he didn't have a Wikipedia page because somebody tried to make one, and Wikipedia said you're not important enough to have a Wikipedia page, and so they took it off and denied her a Wikipedia page, and then she won a Nobel Prize, and it suddenly came back. So I guess a Nobel Prize will do it for you. They have a method for generating high-intensity, ultra-short optical pulses. Her and Moreau, her graduate advisor, Rochester, New York. This is actually interesting technology and fairly important. Their problem was if you try to amplify a short pulse, the peak power of the amplified pulse is so high it destroys the amplifier. And this has been a problem for a long time. And they discovered that if they could stretch the pulse in time, that would lower its peak power. They could amplify the pulse, and then they could recompress the pulse, and now you get an amplified, very high intensity, very short laser pulse. This is the technology, for instance, that's behind laser eye surgery. You have to have a very finely tuned, very high power, very short laser pulse to do it. Excuse me. And her technology is what makes that and several other applications in medicine and industry work, where you need a short pulse with high intensity. And so she became the 3rd woman to earn a Nobel Prize in physics, and she broke the curse of the Marys, because before that it was Marie and Maria, now it's Donna, right? So you can have any name you want now and get a Nobel Prize in physics if you're a woman. Before it was just Mary, right? But we fixed that. And likewise, the Nobel Prize this year in medicine or physiology went to Frances Arnold at Caltech. She has a number of awards, and what she's done is what's called directed evolution, and this is a scheme that describes what you do. Is that you have a sample of DNA with mutations in it, and you run them through fast mutations, and then you weed out the ones you like, and then you run them through the same process until you have a large collection of the variety of bacteria that you want that will grow the enzyme you're looking for. And this allows you to create enzymes that will favor chemical reactions that don't otherwise exist in nature. So we can create non-natural chemistry and non-natural molecules. You can actually create molecules that do not occur in nature, building them with enzymes that are controlled by directed evolution, which opens up all kinds of doors in chemistry and who knows how many applications that she got the Nobel Prize for. Unlike Strickland, who was completely unknown by anybody except her close friends until she won the Nobel Prize, and everybody wants her autograph. Everybody wants her to be on Wikipedia. Arnold was very well known long before, and is laboratory director at Caltech and has a couple of endowed chairs and a large number of firsts for women. And the first woman to receive the Draper Prize from the National Academy of Engineering, first woman to receive the Millennium Technology Prize, and the first woman to be elected in American history to all 3 national academies, the National Academy of Engineering, the National Academy of Medicine, and the National Academy of Sciences. So she was already very well known, and her work is clearly worthy of the Nobel Prize. Speaking of Nobel Prizes, so I have put up here, now this year there was no Nobel Prize in Literature awarded. This is a mistake. This actually goes to 2018, and I forgot to update these 2 numbers, so yeah, in a hurry. But up to 2018, this is what fraction of the prizes have gone to women. And since 1901, so we've got just over 1% in physics and almost 3% in chemistry. If you combine them, you get just over 2% for chemistry and physics. These numbers all the way down the line are obviously very small compared to what you would expect for the fraction of scientists that are women, which leads you to wonder, is it the Nobel Committee doesn't like giving prizes to women? They only give prizes to people who are nominated, so maybe women are just not getting nominated. Maybe women aren't getting the opportunities in research that lead to Nobel Prizes. Opportunities like Strickland and Francis Arnold got. Who knows? I don't really know why these numbers are low, but they're too low to be chance. There's a systematic effect of some kind going on, and I don't know what it is. And I don't know if anybody knows what it is for sure. But clearly, women are not receiving their fair share of Nobel Prizes, one way or another. And likewise, there's no Nobel Prize in mathematics, but the equivalent is the Fields Medal, which has been awarded since the 1930s. I think they awarded it once, and then they waited until 1950 and then sit in their 4-year cycle of awarding the medal, which was last awarded this year, will be awarded again in 2022. This is the equivalent in prestige of a Nobel Prize in mathematics, and out of 60 awards, exactly 1 has gone to a woman, and that was in 2014, last time prior to this that the awards were made, to Mariam Mirzakhani, an Iranian mathematician, who made significant advances in field theory. Same number, 1.67%. Women, the female brain generally is better at mathematics than the male brain, if I may say so. And if you look at secondary education, there's no reason to believe that women or girls are any less capable than boys at mathematics, and sometimes reason to believe they're more capable. It's a little surprising that there would be only 1 Fields Medal. The same effect is going on here. Something is happening whereby women are simply not receiving their fair share of the credit you think they ought to get. And that's my talk. And so hopefully I said something interesting and you learned something worth learning, and you'll invite me back again someday. Thank you. And I'll answer questions until your boss says get the hell out of here.
You left out the gal at, whose name escapes me, I know it well.
And me too.
Who discovered quasars, I mean not quasars, pulsars.
Yes, that's Jocelyn Bell.
Bell, yeah, and she recently got awarded, I think it was $200 million prize from the breakthrough people.
Yeah,
even though she didn't get the Nobel Prize, she's doing well.
There are more women who probably deserve to be in a talk like this than I have time to put into it. Yeah. I picked the ones going back in history, the ones I thought were important. Jocelyn Bell apparently doesn't seem to think that she should have gotten a share of the Nobel Prize. It may seem kind of strange, but in an interview she said that it was proper that the professor in charge of the program get the prize, and if you start giving it out to all the graduate students, everybody, there's just too many people it's the way she answered the question makes it look like she's not bothered by not getting a share of the prize. And all of her public statements are like that. What she thinks privately, I don't know. Whether she wants to go shoot somebody, I can't tell you. But publicly, at least, she does not seem to be bothered by that. And and there are lots of controversies. Why didn't Lisa Meitner get a share of the prize for actually discovering nuclear fission? Hahn did the experiment, but she had to tell him what it was that he saw. And so, perhaps even more so than Bell, she deserved a share of the Nobel Prize because Jocelyn Bell did not know what she had discovered. It was Hewish who figured it out. Meitner, on the other hand, is the one who did figure it out and didn't get a share of the prize. And there are numerous controversies in giving out the Nobel Prize. Not all of them involve women, who should and shouldn't have gotten it. And at least one recipient in, I think it was physiology and medicine, I can't remember his name, but was so mad when the committee did not include his graduate student colleague in the prize that he just gave half the prize to his grad student. And I don't know whether he chopped the medal in half and gave him half or something, but he complained bitterly to the committee afterwards that not fair. Yeah.
I read The Glass Universe, and it's fascinating the plates that the women handle there. I would sure encourage it if there's any interest in how that happened 100 years ago.
Oh, yeah, that book is a really good book. They're all good books. I have two, and I don't have Hidden Figures yet. I do have Rocket Girl, which I now have to read, along with that other stack of books I have that I haven't read yet. And I'm kind of halfway through Sobel's book. All that stuff, in Mount Wilson, it was the same thing. You know, all the old observatories, everything was on a glass plate, and nothing was digital. So remember when Clyde Tombaugh went looking for Pluto, he put his plates on the blink comparator, and he had to stare. He didn't have a microscope eyepiece like Walter Baade had. He just had to look at this image, and look at this image, and look back and forth. Well, he looked at one image as it blinked back and forth. And he had to stare at this corner, and then stare at this one. He had to move and stare at the image to look to see if anything's bouncing back and forth, blinking on and off. So with his eyeball, he probably individually looked at about 8 million different stars. And nobody's ever going to do that again. It's the same thing. It's done by electronic computers these days. And it was a lot more time-consuming. And unlike the search for Neptune, when everybody says, look right here, you'll see it. And it turned out that's what happened. Tombaugh just took the whole ecliptic plane. I'm going to take this big chunk of sky and look at everything. And if it's there, I'm going to find it. And eventually he did, and he found some galaxies and comets and a whole bunch of other stuff.
Wow.
It was back in the old days when astronomers, were really tough. Yeah. You had a question?
Since the Nobel started, the population of the world has quadrupled, plus the number of people who were highly educated is far greater than quadrupled. And it seems to me that its minuscule selection of half a dozen or a dozen is almost irrelevant in our society because of the vastness we have. So isn't there another test we could, for instance, I know that with one of the organizations I've been involved with, that the number of female scientists in it, in fact I was counting and I brought the proof that of 40 total scientists being funded by Planetary Science Institute, 17 are women. And that is a vast increase over what it was even 10 years ago. So I wonder if the number of women in graduate programs and professorial programs, research, flat-out research positions in NASA and aerospace companies, isn't a far better judgment, test, whatever, measure of the increasing importance and involvement and interest of women in astronomy.
It almost certainly is, in fact, a better measure of women's involvement and interest. I particularly mention the Nobel Prize because they probably have the highest profile of any academic prize. But there's a bunch of other very high-level prizes like the Kyoto Prize or the Crayford Prize or the Gold Medal from the Royal Society, the Copley Medal, and a number of other prizes like the Fields Medal. And these are the things that get you elevated to higher academic positions. Like if you want to become an endowed professor or get a named chair or something like that, well, a Nobel Prize or a Crayford Prize or something will push you up there. And so it's an indication, all these prizes, and of course a lot that I didn't look at, are indications of very high-end achievement recognized by peers. You have to be nominated to get these prizes. And a Nobel Prize, okay, if you don't get nominated, you don't get it, you may deserve it. And so, certainly looking at the population is a fair assessment, but you want to look at the vertical mobility of that population. How many of those women have achieved senior positions, elevated positions? There may be a lot of women in academia, but how many of them are full professors? How many of them are endowed professors? How many of them get the academic prizes or edit important journals, things like that? And I think the imbalance begins to show up when you look at that high end, where somebody else has to decide you're worth doing this. You get a degree by doing something yourself. You achieve that, and you do the work and you get the degree. But when you go beyond that, for a lot of these other positions, somebody else has to decide, I'm willing to nominate you for that job. I'm willing to put you in that job. And their attitude towards you has a whole lot of things mixed into it. They like you or they don't like you. Are you a man or a woman? Are you Polish? Are you from down the block? If you're one of those people from the other side of the lake, let them over here, right? Come on. and so that all plays into it somehow. And that's why I think you have to look across the board. If you look at the Fields Medal, the Nobel Prize, you can do the same thing, the Kyoto Prize or the Crayford Prize. Look at all of these high-end prizes. And in every case, the number of women is minuscule compared to the number of men. And that, to me, is a systematic effect that has something to do with choice. If you look at the pool, there are plenty of women to choose from, but they're not getting chosen. And that's kind of the point. The whole affair is, yeah, you're right, there is this big pool, but why is it if there's almost as many men as there are in women down here, there's one woman up here and a whole bunch of men? There's something wrong with that. Yeah.
Let me postulate another point here, though, is that in all these honors, there's a generation gap.
Mm-hmm.
Like the Nobel is honoring things for people for things done 20 years ago. And the federal anti-discrimination is 75.
Yeah.
So that would indicate about 95 is when we should see it increase. It'd be interesting to see somehow these honors. There's something about the time scale here that's
yeah,
not right.
I suspect that you won't see much of a difference there. I don't really know how to assess it with time. I looked at some of these prizes, and like Strickland, the last Nobel Prize in Physics before Strickland was in the 60s. That was Maria Geppert-Meyer. It was 50 years later, you get another woman. That's quite a long gap. My guess is if you try to look at the time distribution, you probably won't see much of an effect. Yeah.
I was just going to mention, you really focused on academia
I
here,
did.
but we're talking about space and astronomy, and so I think Gwynne Shotwell of SpaceX is probably worthy of a mention. I would expect her to earn a Nobel Prize being in an industry position like that, but seems that she's been pretty instrumental at SpaceX.
Yeah, there are women in entrepreneurial positions that it's much harder to assess. And my knowledge, of course, is in this area. I don't really know much about entrepreneurial. I wouldn't know how to look through and say, okay, which one of these women has achieved a big thing and which one has, I don't know which companies, which are or aren't worthy of inclusion. My guess is if you look at the entrepreneurial environment, you'll find a better representation for women than you do in the academic environment, but I think you'll find they're still significantly outnumbered by men. But that, like I said, that's only a guess because I haven't looked at the entrepreneurial environment. And like I said before, I could keep you up until 2 or 3 in the morning. If I put all the women on here that could be talked about, you get out finally and say, shut up and go away. So,
I think Admiral Hopper was the lady that said it's better to ask for forgiveness than permission.
That wouldn't surprise me, especially coming from a Navy admiral.
Yes.
Yeah, well, she kind of had to do that because nobody believed her when she wrote her compiler. And she
just go for it.
Just keep going, yeah.
Good talk, really good.
Yeah, thank you.
Yes.
Anything else? Cool.
Wonderful.
I hope your son wasn't too bored.
No. You got some good nuggets there.
Thank you.
Okay, thanks everybody for coming. Let's see, coming up next month we'll have Scott Roberts from Explorer Scientific talking to us. We're not sure exactly what the topic's going to be. Something I suggested, something about the future of amateur astronomy, and I definitely told him it was not outside the bounds to make some plugs for his own products just in time for the Christmas shopping season. As always, December we will not have a lecture. Instead, we'll be having our annual solstice party. I just did corner our talk for January. A speaker we've had before, Don Jennings, who spoke before on the Cassini probe. His group also developed a spectrometer for New Horizons. He has agreed to come back in January and just gave this talk to us here at the observatory. But I cornered him and twisted his arm to talk to us about, reprise that talk and update it just after the New Horizons encounter with the trans-Newtonian object, the Kepler, whatever, the MU-76 or something. I don't remember what the name of the object that's going to encounter. So we will get fresh off the presses talk about the New Horizons encounter. And I found his talk fascinating from a hardware standpoint, talking about how they got a spectrometer, basically a spectrometer onto a chip to fit it onto a budget for the entire spacecraft, which was something like 100 kilograms, something like that. It had to be incredibly lightweight. Interesting talk. So thank you for coming, and we'll see you back next month.
Very good.
Thank you.